Contractions of a whole muscle show variations in the development of tension. For example, the same muscles that can lift a potato chip can also lift a six-pack of soda. Your goals for learning are to examine the component parts of a single muscle contraction, to understand the relationship between muscle tension and frequency of stimulation, motor unit recruitment, and degree of muscle stretch. Here's what you need to know. The sliding filament theory of muscle contraction. The definitions of slow twitch fibers and fast twitch fibers. The definitions of motor unit and recruitment. A whole muscle does not respond to stimulation in an all or none fashion. Instead, it shows variations in the development of tension or force of contraction. In this topic, we will examine three factors which affect muscle tension. 1. Frequency of stimulation. 2. Number of motor units recruited. And 3. Degree of muscle stretch. We will begin our study of whole muscle contraction by looking at how a muscle responds to a single stimulus by making an isometric contraction. A muscle contraction in response to a single stimulus of adequate strength is called a muscle twitch. Click the stimulator button to elicit a muscle twitch. The graph shows a tracing of the muscle contraction. The short vertical line marks the time when the stimulus was applied to the muscle. If you would like to see this animation again, click the stimulator button. A complete muscle twitch is divided into three phases: latent period, contraction period, and relaxation period. The actual time periods for the three phases shown here may vary with the specific muscle being studied. Click each region of the graph for more information. When a second stimulus of the same intensity is applied to a muscle before the completion of the relaxation period, a second contraction occurs, adding its effect to the contraction resulting from the first stimulus. This is known as temporal summation or wave summation and results in increased muscle tension. The stimulator has been set to give two stimuli to this muscle. Click once on the stimulator button to see the response to a double stimulation. Notice that the second peak is higher than the first. Since the muscle is already partially contracted from the first stimulus, the additional influx of calcium ions promotes a second contraction, which is added to the first contraction. Now predict how the time interval between stimuli will affect the height of the second contraction. Click and drag the slider bar to each time interval, make your prediction, and then click the stimulator button to see the effect. Now select another time interval. Now select another time interval. What do you think will happen if you wait 110 milliseconds before stimulating a second time? The height of the curve will be the same as at 90 milliseconds. The height of the curve will be less than the first contraction. The height of the curve will be equal to the first contraction. Why is the height of the curve equal to the first contraction? Cross-bridge cycling has stopped. There is no activity to be summed. The calcium ions from the first contraction have already been actively transported back into the terminal cisternae. Both of the above. That's correct. Calcium ions from the first contraction have already been actively transported back into the terminal cisternae. Since the muscle is no longer partially contracted, a temporal summation is not possible. Now observe the following situation. A muscle is repeatedly stimulated. The interval between stimuli is gradually decreased. All stimuli are of equal intensity or voltage. The stimulator has been set to send a series of stimuli to the muscle. Click the stimulator to see how the muscle responds. The resulting graph shows several aspects of the mechanical activity of muscles when the frequency of stimulation is altered. The phases of this graph include trepa, temporal summation, incomplete tetanus, complete tetanus, and fatigue. Click on the label for each region of the graph for more information. With increased frequency of stimulation, the muscle exhibits shorter contraction-relaxation cycles. This condition is called incomplete or unfused tetanus. Note that some degree of relaxation is visible after each contraction. Click the stimulator to see muscle activity during incomplete tetanus. Then click another region of the graph. With rapid multiple stimulation, the contractions fuse into a smooth, continuous total contraction without evidence of any cyclical relaxation. The muscle is now in a state of complete or fused tetanus. Abundant intracellular calcium provides continual availability of binding sites on actin for cross-bridge cycling. Click the stimulator to see muscle activity during complete tetanus. With continued rapid stimulation, fatigue becomes apparent as the muscle is no longer able to sustain its level of tension, but gradually elongates. Fatigue is due to multiple factors: buildup of acidic compounds which affect protein functioning, a relative but not total lack of ATP, and ionic imbalances resulting from membrane activities. With rest and adequate blood supply, fatigue conditions are corrected, and the muscle will again be ready to respond to stimulation. Click the stimulator to see muscle activity during fatigue. Then we have just examined how the frequency of stimulation affects the development of muscle tension. We will now explore the relationship between the number of motor units recruited and the strength of contraction. The strength of a muscle contraction is determined not only by the frequency of stimulation, but also by the number and size of motor units recruited. In vivo, the number of motor units that are recruited is determined by the number of motor neurons that are stimulated by the central nervous system. By varying the number and size of recruited motor units, the nervous system can control the degree of contraction of a particular muscle. Click the button to begin a demonstration on this concept. To see the relationship between number of motor units recruited and strength of contraction, first, click one of the black weight bars to be lifted. Next, click and drag the slider bar to recruit different numbers of motor units. Then, click the thigh muscles to see their response to each level of work. In the laboratory, the number of motor neurons being stimulated to recruit motor units cannot be easily controlled. Instead, the stimulation voltage is increased to recruit more motor units.